Hi, I'm Carlton Coffrin. In this video, I'll give you a brief overview of PowerModels.jl, which is a Julia package that we've been developing recently for doing power system optimization. I would like to emphasize, although I'm the person giving this talk and preparing this talk, this has really been a collaborative effort among many different people that have contributed to a lot of the ideas and results that are in this presentation. So why are we building this Julia package? The primary motivation is that there has been an explosion of power flow formulations in recent years. So these include approximations like the LPAC model, or relaxations such as SOC, QC, SDP, the moment hierarchy. There's really quite a lot of options here. In 2014, I did a brief survey and taxonomy of all the different methods I could find on how to formulate the power flow equations, and I was able to find over 30 different approaches. If you focus in on just the relaxations at that time, there was more than 8 approaches, and now there's probably twice as many as that. So there's really just been an incredible amount of different work done here and different ideas being proposed for how to address the power flow equations. So this explosion of different formulations has presented a number of challenges. The first significant challenge is, how do we compare these formulations? It's not always obvious when you read the papers if the formulations being studied have used the same equations. It's not clear if they've used the same constraints. It's not clear if they've used the same objective functions. And last but not least, they're usually implemented in many different languages like MATLAB, Python, or mathematical modeling layers like AMPL. And so doing a direct runtime evaluation is very difficult because the various overheads of these different languages can impact those results. The next major challenge is that one formulation does not fit all problems. So when someone's picking up a new type of problem, they may want to try a lot of different approximations or relaxations of that problem before they can really hone in on what the right answer is for their particular use case. And so users may not want to know the details of these things, but they'll need to explore many of them very quickly. The last technical challenge has to do with the implementation details of these models. Some of these models can be very complex and sophisticated in their implementation. So for example, the QC model, when you look at the voltages on branches in the network, you have 14 different constraints which you need to implement correctly. And one typo can basically break the relaxation property of that particular method. So because of these details of some of the more complex methods, implementation is best provided by the authors who are designing the methods and really know all of the technical details in a lot of depth. So to help address these challenges, we had 3 core ideas. The first one was to develop a power system optimization modeling software, which can be formulation agnostic. And what does that mean? It means that all the different formulations are going to share a common problem specification so that we know that they're consistent in the set of equations and the set of constraints that they're going to be solving. This also means that it should be very easy to switch formulations because all the software engineering is going to do that for you, and all you need to do is think about your abstract problem specification and then select which formulation you would like to use. The next major idea was that the code should be open source and community driven. So this means that formulation authors should be contributing their implementation to the master code repository. And the main goal here is that those formulation authors are most well suited to provide the best possible version of their particular idea, and they can contribute it directly into the common platform. The last core idea was that if we have a common implementation platform, we have shared problem specifications to ensure the same equations and constraints, then we can do side-by-side comparisons of runtime and other kind of benchmarking metrics which are much more accurate because we've already controlled for the programming language and the modeling layer and all of those pieces. So combining those 3 ideas is what PowerModels.jl is. It's an open source Julia package for power system optimization where you can explore these formulations, different formulations of shared problems very quickly. So I'll tell you a bit more about this. Why did we pick Julia? There's many of languages out there that we could have picked. The first and foremost reason was the lanl postdoc revolt of 2014. This particular incident was basically that all the postdocs working in our group at Los Alamos decided they would be using Julia, and there was nothing that the rest of the staff could do about it, so we just all started using Julia. Now, there were some good reasons for why the postdocs insisted that we all be using Julia. The first one is that Julia is a language that is free and open source. It's designed for scientific computation, and it's striving to be the best of MATLAB, Python, and C. So it kind of suits R&D in power systems very well for all of those reasons. It's a type of scientific computation. We want kind of MATLAB-like syntax, but with all the nice features of languages like Python and C. The second major motivating reason is that there is a modeling layer called JUMP in Julia, which is a fantastic optimization modeling language that supports a wide variety of different solvers. So you have things like linear programming, second-order cone programming, semi-definite programming, nonlinear programming, and the mixed integer variants of all those different problems. So this is one of the few modeling languages that spans all of the different problem classes that we have encountered in power systems formulations. And it made an ideal candidate for really exploring these in a common platform. Maybe a less appreciated but very valuable feature of Julia is that it has a built-in package manager, which you can use to pull down code and getting it running on your computer. So if you have Julia installed and you want to use PowerModels, all you have to do is package.add PowerModels, and it knows where to find the code. It's going to bring it down and install it on your computer. And this is a really huge advantage of using Julia. So what is PowerModels? This is the pictorial version of what PowerModels is. There are optimization, modeling, or solving softwares which are typically written in C and C++. Many of us access those through modeling languages like Julia or MATLAB. And then on top of that base language, we have another layer of, say, optimization modeling, which in Julia is called JUMP. In MATLAB, it would be called YAML or CVX. And then on top of that, we have our infrastructure-specific modeling abstractions. In MATLAB, it's called MatPower, and in Julia, we're calling it PowerModels. So right now, what kind of features does PowerModels have? There are data parsers for MatPower files and PSSE version 33 files. We have problem specifications for the classic problems that you have, like power flow, optimal transmission switching, and a few more. We also have standard formulations for different power flow problems. So you have the AC in polar form, the AC in rectangular form, the DC power flow with line losses, and then second-order cone relaxations and a variety of other relaxations. There are also extension packages for PowerModels, like PowerModels Annex, PowerModels Reliability, and OPF Recourse, and hopefully there'll be many more extension packages in the future. So that's kind of the state of affairs of what PowerModels is right now. I'll give you an intuition of how it works by just a simple OPF study. So you need to install both PowerModels and a solver, which can help you solve the models. We're going to install the solver called IPOpt because you can use it for both continuous convex and non-convex problems. So if you want to install PowerModels, you just do package add PowerModels and you do package add IPOpt to get that solver down. Now let's load in a data file. First, you use the command using PowerModels to bring in the modeling package and all the related functions. The function to read in a data file is called parseFile, so you just give it a string and it'll look at the file extension and try to parse it using that particular data format. Then you get this object called network data. The easiest way to see a summary of what's in the network data is the PowerModels print summary function, passes the network data, and it'll give you a table-like representation of what data is in there. Now, natively, the network data in PowerModels uses a nested dictionary structure. So if you want to investigate a particular element, you just look up, say, the network data, the bus table, the bus with ID 1, the VA value, and then you print that to the terminal, and you're going to see exactly what the angle is in that particular data set. Now let's say you're done looking at your data, modifying, understanding your data. You want to solve a traditional optimal power flow problem. You using IP-opt to bring the solver into the current session. Then you can use a command like run ACOPF. You give it one of these network datas. You pass it the IP-opt solver, and it's going to set up an ACOPF polar formulation. It's going to solve it, and then it's going to give you a result object. If you want to see what's in that result object, you can do print summary AC result solution, and you'll see a nice summary of what's going on there. If you want to do, say, a DC power flow, you can use run DCOPF and with a similar kind of structure. Now, the question becomes, how do you vary the problem formulation? That's one of the core design features of power models. So I just showed you this example of doing an AC or a DCOPF. Both of these functions are really shorthands for a more general function, which is called run OPF. Now, run OPF takes a network data model, a formulation parameter, and then the solver. So this is where you can start to see that there's a shared problem specification. All of these different formulations are going through the common run OPF function. And actually, all run DCOPF is a shorthand for running OPF with this particular parameter DCP power model. And then AC is just with ACP power model. So this is a non-convex model that you can solve with IP-opt. This is a linear approximation, which you could solve with IP-opt or a linear programming solver. And this is a convex relaxation, which you can also solve with IP-opt, but you could also send it to a dedicated convex solver. So this is how you can kind of switch this OPF formulation between these different types of forms. So what about varying the problem class? Let's say you don't want to solve the optimal power flow problem. Well, there are different function names for every one of the problems that are supported. So this is the problem class. So you have things like power flow, optimal transmission switching, and then this is the problem formulation. So if you want to, say, take one of these particular problem classes and then get a linear approximation of it or a convex relaxation of it, you just take the same function and you apply the correct parameter for what formulation you'd like a linear one or a convex one. And there are different names for all sorts of different formulations. Let's dive in and see, how does that run OPF function really work? There is hidden in there another function which is called post OPF. This is the function which sets up the mathematical model you're actually trying to solve, and it's totally formulation agnostic. So this is the actual code that's in PowerModels currently, and this is an example of the kind of mathematical model that I would write in a paper to describe this problem. And I think the beautiful thing here is that there's basically a one-to-one mapping between the functions that you're seeing in this OPF modeling layer and the kind of expressions you'd write in a mathematical version of the problem. It's also interesting to note that, like, when I was doing this mapping, it made me realize that there are two things I usually define in my formulations: the variables on the branch flows and also the reference bus constraint, which are kind of implicit in the academic papers I write. But inside of a code base, you can't have anything that's implicit. You have to be explicit. And this really helped me remember that there are some details to my implementation I usually don't write in my papers. And the key point here is that I've explained to you this whole OPF problem. I've shown you a mathematical formulation, an abstract mathematical formulation for it, but we haven't really gotten into the specific formulation we're using. Is it polar form? Is it rectangular? Is it DC approximation? We haven't gotten into that. So you're actually seeing an abstract version of the OPF which isn't specific to any one formulation. Another interesting thing about this modeling layer is how can you model other problems. So here's a compare and contrast of what the OPF problem looks like compared to what the OTS problem looks like. So what is the key changes here? We're going to add some new variables. We're going to have an indicator variable for each branch because you're going to turn on or off the branch with like a 0, 1 variable. And then for the voltages and all of the branch constraints, we need these on-off variants so that they know they should use the indicator variable to adjust their state. But I think the valuable thing here is that a significant chunk of this model is an exact replica of what we have in the OPF problem. So all of Kirchhoff's current law, all of the reference bus, the objective function, the generator variables, this is all consistent with the OPF formulation. And so if you're only making a very small change to the problem, like changing the objective function, there's very little you need to change to make a new formulation. Now, how can this formulation swapping work under the hood? A detailed explanation would take quite some time, so I'll give you an intuition for how it works. You can have this notion of, say, a variable product, vi times vj, and not really know how it's implemented. Is it a polar form? Is it rectangular form? It's just a product of two complex numbers. And so what PowerModels is doing is when you say, I want the ACP power model, it's going to go through and use different functions to basically replace the vi times vj star with this particular real number implementation of that expression. So one where you're using voltage magnitudes and cosine and sine terms. If you say you want the ACR power model, what it's going to do is introduce new variables for rectangular voltage variables, and then replace with these more complex expressions for voltage products. If you say you want the ACT power model, it's going to do something even more complicated. It's going to lift the VI, VJ expression into a higher dimensional space of WR, and WI. Then it's going to post two constraints, one which is like a kind of a quadratic constraint and one that's this tangent constraint. And it's going to set up the whole power flow problem doing this substitution. Then if you do something like a DCP power flow model, it's going to take the real part and make it 0 and then replace the imaginary part with just the difference in the phase angles. So this gives you some kind of intuition for how you can start with a very abstract specification and on a case-by-case basis replace it with something else. So in this paper, we did a validation study to compare the power model's implementation to MapPower, and we also did an ACOPF formulation swap study to kind of show how you can use the framework to do a benchmarking comparison of different approaches. So this is nominally the program we're using for the formulation swap study. We load in a common data file, and then we call run OPF with different formulation parameters like AC polar, AC rectangular, AC tangent, and then some relaxations. So one thing that's interesting here is that all of these non-convex forms, AC polar, AC rectangular, AC tangent, are mathematically equivalent. So we expect them to kind of get similar results. But these two formulations are convex relaxations, so we expect them to actually provide a lower bound to all of the solutions provided by those non-convex models. How we're going to benchmark these is we use these IEEE PS PGlib OPF test cases, which are available on this particular website. We focused on the cases with more than 1,000 buses because the ones with less were all kind of so fast it was not easy to see any difference in the different methods. So here is the validation study. The key things you need to know about this table is that MP stands for MapPower, PM stands for Power Models, ACP is the AC polar formulation, and DCP is the DC power flow formulation. So I'll just highlight some key results from the table that appears in the report. The first thing we observed is that the AC solutions are identical when MapPower converges. So if you look at the objective function in both MapPower and Power Models and the AC model, they're going to be identical every time MapPower converges. The next thing you'll notice is that MapPower's default solver can be very fast, but it is less reliable. So there are these cases where it'll converge, it'll say no solution found very quickly, but IPOPT, which is the one we're using in Power Models, is finding the solution, like a solution to the problem. There are some minor differences in the way the DC power flow implementation is done in both Power Models and MatPower. And so you can see that the objective functions in the case of the DC model are slightly different, but they're very close. So this is kind of expected difference that seems reasonable. For the formulation swap study, we have 5 different formulations we're looking at. We're going to use the AC polar case as kind of like our base case formulation. And then for the AC rectangular and theta W formulation, we're going to compute the absolute difference of the objective function against the base because we expect these to be the same. And then for the relaxations, we're going to compute an optimality gap because these are lower bounds, so that's a meaningful metric. So here's a summary, like highlighting some of the key results from this table. The first thing is that all of the non-convex formulations converge to the exact same objective value, up to the solver's numerical tolerance. So when you look at this table, you'll see a few like minor differences, but it's in like the 8th decimal place of the objective, which we weren't even optimizing to that level of quality. So this means these 2 values are identical for all numerical purposes. The next point is that the relaxations are always providing a lower bound, and this is exactly what we expected. If we saw any negative values in this table, it would indicate there was a bug in the implementation, so that looks nominally good as well. An interesting observation is that of all the non-convex formulations, the AC rectangular form seems to be the fastest non-convex formulation. We looked into this in a little bit of detail and observed that it seems to be because the derivative computations for that formulation are very fast. So it's not that like the number of iterations is going down, it's just that you can compute the derivatives a lot faster when you're in a purely quadratic model, even if it's non-convex. And it's worth noting that this rectangular form being the fastest was also observed in this 2013 technical report. So this is another validation which seems to indicate that the implementation is correct and is showing similar results to the literature. So to conclude this very brief overview of what PowerModels is, there are a lot of PowerFlow formulations out there. It's really not clear which ones are the best and which ones we should be using for different types of problems. So we have proposed PowerModels to help researchers explore which formulations are best for them and to contribute new formulations. We're hoping we can use this to rigorously benchmark formulations with a shared problem specification and a shared computational platform to get a lot more insights into how to use all these different methods. As a bonus, we have now a completely free and open source toolchain for doing PowerFlow studies and optimal PowerFlow studies, which is very nice for HPC if you want to run hundreds or thousands of jobs in parallel. We have a very nice and robust MatPower parser in Julia, a very nice and robust PSSE parser in Julia, and now there's a reference implementation for kind of the base OPF and PowerFlow equations in Julia, which can be used for future works. So I'll just, as a final remark, say thanks to all of the contributors to the code base. It has been a very collaborative effort, and I hope that collaborative group will continue to grow. So thank you much for listening to this talk. I hope you enjoyed PowerModels, and if you're interested in more detail, there's a lot of documentation online. Please read through it and send questions. We're always happy to answer them. Thank you very much.